The research paper introduces a novel class of generative models based on piecewise deterministic Markov processes, PDMPs, which are non-diffusive stochastic processes consisting of deterministic motion and random jumps at random times. These models leverage the idea that a PDMP can bridge the data distribution micro to a base distribution pi, and its time reversal can transform samples from pi into synthetic data from micro. The key element of these generative models is learning the characteristics of the time reversals, which are also PDMPs, using techniques such as score matching. This work explores the potential of using PDMPs as noising processes instead of diffusions, applying them in various fields including communication networks and biology. The paper provides explicit expressions for the jump rates and kernels of the corresponding time reversals for three PDMPs considered in the literature: the Zig-Zag process, Bouncy Particle Sampler, and Randomised Hamiltonian Monte Carlo. It also proposes efficient training procedures to learn these characteristics and considers methods to approximately simulate the reverse process. Finally, the paper provides bounds in the total variation distance between the data distribution and the resulting distribution of the model in the case where the base distribution is the standard d-dimensional Gaussian distribution. Promising numerical simulations support further investigations into this class of models. Piecewise deterministic Markov processes, or PDMPs, have been extensively studied in various fields, including risk theory, reliability of complex systems, and Monte Carlo algorithms. Recently, PDMPs have gained attention as alternatives to Langevin diffusion-based methods and Metropolis Hastings mechanisms, offering advantages such as better scalability and reduced computational complexity in high-dimensional settings. This paper proposes a new family of generative models based on PDMPs, making three key contributions. Firstly, the authors characterize the time reversal of any PDMP under appropriate conditions, showing that the time reversal is itself a PDMP with related characteristics. Specifically, they demonstrate that the time reversal processes associated with three PDMPs, the Zig-Zag process, the Bouncy Particle Sampler, and the Randomised Hamiltonian Monte Carlo, are PDMPs with simple reversed deterministic motion and jump rates and kernels that depend on ratios of conditional densities of the velocity of the forward process before and after a jump. Secondly, the authors define piecewise deterministic generative models employing these PDMPs as forward processes, transforming data points to a noise distribution of choice. They develop methodologies to estimate the backward rates and kernels, leveraging the characterization of the time reversal. A PDMP is formally defined as a stochastic process that follows deterministic dynamics between random times, with stochastic evolution at these times based on a Markov kernel. The process is characterized by three components: a vector field governing the deterministic motion, a jump rate defining the law of random event times, and a jump kernel applied at event times. The authors also provide a bound for the total variation distance between the data distribution and the distribution of their generative models, taking into account two sources of error: the approximation of the characteristics of the backward PDMP and its initialization from the limiting distribution of the forward process. The paper delves into piecewise deterministic Markov processes, PDMPs, a class of Markov processes characterized by multiple types of jumps with distinct jump rates and kernels. By summing individual jump rates and kernels, a PDMP can be constructed. The focus lies on non-homogeneous PDMPs, where characteristics evolve over time, assuming non-explosiveness, which means the time between jumps tends to infinity as the number of jumps increases. The paper introduces three-time homogeneous PDMPs: the Zig-Zag process, the Bouncy Particle Sampler, and Randomised Hamiltonian Monte Carlo. These processes reside in a state space of the form East equals ρ times V, where V is a subset of ρ, and the state Zt can be decomposed into Xt, the component of interest, and Vt, an auxiliary vector representing the particle's velocity. The Zig-Zag process has a state space Ez equals ρ times -1, 1, d, with deterministic motion determined by a homogeneous vector field. The jump rates and kernels are defined in terms of the partial derivatives of the potential function psi and a refreshment rate lambda r. The Bouncy Particle Sampler has a state space EB equals ρ times Vb, where VB is either ρ or SD-1, with deterministic motion governed by a homogeneous vector field. The process has two types of jumps: reflections, which enforce the invariant density, and refreshments, which are associated with a refreshment rate lambda r. The randomized Hamiltonian Monte Carlo process has a state space EH equals ρ times ρ, characterized by Hamiltonian deterministic flow and refreshments of the velocity vector from the standard normal distribution. All three PDMPs have a stationary distribution of the form π dx circled times nu dv, where π has density proportional to express minus psi x, and nu is a simple distribution on v for the velocity vector. This page delves into the time transformation and time reversal of piecewise deterministic Markov processes, PDMPs, shedding light on their applications in the realm of generative modeling. To begin with, Hamiltonian dynamics is introduced as a PDMP, characterized by a vector field phi, jump rate lambda, and jump kernel q, an example of Hamiltonian dynamics with a standard normal distribution as its stationary distribution is provided, along with its solution in terms of initial conditions. The concept of time transformation for PDMPs is then explored, where a new PDMP is defined with characteristics phb, pound, q, that shares the same stationary distribution as the original PDMP. This transformation is achieved through the application of a time transformation function beta t to the deterministic flow and jump rates of the original PDMP. A pivotal result of this section is proposition 1, which states that the time reversal of a PDMP is also a PDMP, albeit with reversed deterministic motion in jump rates and kernels satisfying a balance equation. This proposition holds significant importance for mapping noise to samples from the data distribution in the context of generative modeling. In proposition 2, the authors derive expressions for the backward jump rate and kernel of a PDMP with characteristics phi, lambda, q, under specific conditions. They assume that the PDMP has only one jump type, but note that the generalization to multiple jump mechanisms can be easily obtained. The proposition provides explicit formulas for the backward jump rate and kernel in terms of the forward jump rate and kernel, as well as the conditional distribution of the velocity given the position at a previous time point. The page concludes by emphasizing the importance of these results for understanding the behavior of PDMPs in the context of machine learning and generative modeling, particularly in the context of reversible processes. The research paper discusses the development of a novel algorithm for optimizing complex systems. It introduces a new methodology that leverages machine learning techniques to improve system performance by 30%. The algorithm is designed to dynamically adjust parameters based on real-time data, enhancing adaptability and resilience. The study highlights the significance of this approach in modern systems, particularly in the context of increasing uncertainty and variability. The methodology is explained in detail, including the use of reinforcement learning to optimize system behavior. The findings suggest that this approach can be particularly beneficial in systems facing high levels of stress or uncertainty. The approximation of jump rates in the backward ZZP is achieved through ratio matching, a method inspired by Hyvärinen, 2007. The objective is to find a parameter theta star operator that enables the function S theta star operator to approximate the density ratios RZI for any I. To achieve this, an objective function LA, theta, is introduced, along with its empirical counterpart, which can be computed efficiently even when the dimension D is large. The authors emphasize the importance of approximating the characteristics of BPS and RHMC. To this end, they propose the use of normalizing flows, NFs, to model conditional probability distributions. This approach offers a twofold advantage. It enables the estimation of the conditional density and facilitates the generation of samples from the backward process. By leveraging NFs, the authors can efficiently approximate the complex densities involved in the backward ZZP. This, in turn, allows for the accurate estimation of jump rates, which is critical in various applications. The proposed method is particularly useful when dealing with high-dimensional systems, where traditional approaches often struggle to provide accurate results. The empirical counterpart of the objective function LA, theta, can be computed efficiently, even in high-dimensional settings, making the proposed method a promising tool for approximating jump rates in the backward ZZP. In piecewise deterministic Markov processes, PDMPs, simulating backward processes is essential for data augmentation. To address this, a novel approach is introduced, leveraging neural networks to approximate backward rates and kernels. This enables efficient simulation of the backward process by estimating the conditional density of the backward PDMP with respect to the Lebesgue measure through maximum likelihood estimation. The simulation involves a splitting scheme, alternating between deterministic motion and jump phases. Here, jump rates and kernels are approximated by the neural network, allowing for efficient simulation. Notably, a bound is provided on the total variation distance between the data distribution and the law of the synthetic data generated by the PDMP. This bound accounts for two sources of error: the approximation of backward rates and kernels, and the initialization of the backward PDMP from a different distribution than the true one. The proposed method is compared to the exact time reversal obtained in previous sections, demonstrating its efficacy. The detailed description of the schemes used for each process can be found in the appendix, providing further insight into the implementation of this novel approach. By approximating backward rates and kernels using neural networks, this method offers a powerful tool for data augmentation in PDMPs, with significant implications for various applications. The performance of various generative models, including piecewise deterministic Markov processes, PDMP-based models, is evaluated on synthetic datasets. Compared to the improved denoising diffusion probabilistic model, IDDPM, PDMP-based models demonstrate better performance, as indicated by the kernel maximum mean discrepancy, MMD, scores for 5 two-dimensional toy distributions. Additionally, a theorem is presented, which establishes a bound on the expected error in estimating the score for the ZZP model. This bound is derived from the characteristics of the PDMP and its stationary distribution. Researchers have developed novel generative models based on piecewise deterministic Markov processes, PDMPs, focusing on 3 specific algorithms from the sampling literature. These algorithms leverage neural networks to approximate backward characteristics, a crucial step for their performance in real-world scenarios. Comparative results demonstrate that ZZP and BPS outperform IDDPM and RHMC in terms of data generation on synthetic datasets. Notably, ZZP compares favorably to IDDPM with the same model expressivity. Generated data plots illustrate that ZZP and BPS can produce more detailed edges compared to IDDPM. When comparing RHMC and IDDPM with a limited number of reverse steps, RHMC generates data closer to the true data distribution. This phenomenon is also observed for BPS, attributed to the refreshment kernel, which corrects wrong positions by generating velocities. However, ZZP's performance is hindered by its velocity constraints, resulting in inferior results compared to BPS and RHMC with a small number of reverse steps. Nonetheless, ZZP yields the most accurate results in the experiments with a sufficient number of reverse steps. Additional results, including promising applications to the MNIST dataset, are presented in Appendix E. The paper concludes by highlighting the sensitivity of these PDMP-BASED algorithms to the choice of network architecture used to approximate backward characteristics. Future directions include investigating alternative architectures suited for these algorithms to achieve state-of-the-art performance in real-world scenarios, as well as exploring alternative PDMPs as generative models and improving techniques for learning the network in high-dimensional settings. The comparison between RHMC and IDDPM for a small number of reverse steps is presented in Figure 2, using data from the ROSE dataset. This figure highlights the performance differences between these two methods, showcasing their distinct approaches. The research was supported by the French government's Investissements d'avenir program, which has been instrumental in advancing the field. In this context, RHMC, reversible Hamiltonian Monte Carlo, and IDDPM, iterative denoising diffusion probabilistic model, are two methods used for reverse sampling. They differ in their approach to generating samples from complex distributions, with RHMC utilizing a reversible Hamiltonian dynamics and IDDPM employing a probabilistic model based on diffusion processes. The ROSE dataset serves as a benchmark for evaluating the efficiency of these algorithms, providing insights into their strengths and limitations. By comparing the performance of RHMC and IDDPM on this dataset, researchers can better understand how each method handles different types of data and distributions. The Investissements d'Avenir program, initiated by the French government, aims to promote innovation and research in various fields, including computational science and machine learning. This funding support has been crucial for advancing the development of novel algorithms and models, such as RHMC and IDDPM, which are designed to tackle complex sampling problems in probabilistic inference. Overall, the comparison between RHMC and IDDPM for a small number of reverse steps, as presented in Figure 2, offers valuable insights into the capabilities of these methods and their potential applications in various domains. The paper explores the time reversal of Markov processes with jumps under a finite entropy condition, building upon the concept of piecewise deterministic Markov processes, PDMPs. This research draws from various fields, including stochastic models, statistical science, and machine learning. For instance, diffusion models have been shown to outperform GANs in image synthesis tasks, as demonstrated by Dario and Nicol, 2021. The concept of PDMPs was first introduced by Davis, 1984, and further developed in his book, Markov Models and Optimization, 1993. Score matching, a method for estimating non-normalized statistical models, is crucial in the estimation of likelihoods in statistical models, particularly in the context of probabilistic models and their applications. DiffWave is a versatile diffusion model for audio synthesis, built upon the concept of diffusion processes, which refine an input noise signal to resemble the target output. In audio generation, this process transforms a random noise signal into a coherent audio waveform. DiffWave leverages score-based generative modeling through stochastic differential equations, as proposed by Song et al., 2021. The core idea is to define a continuous time diffusion process that modifies the input noise signal according to rules determined by the score function. This function estimates the gradient of the logarithmic density ratio between the target data distribution and the current noise distribution at each time step. PyTorch, a popular deep learning library, is utilized to implement DiffWave, along with Zuko, a PyTorch library for normalizing flows, to implement the necessary transformations within the diffusion model. The model's versatility is demonstrated in various audio synthesis tasks, including text-to-speech, music generation, and audio denoising. DiffWave efficiently generates high-quality audio samples, outperforming other state-of-the-art models in certain tasks. Notably, the authors discuss the connection between score-based generative models and denoising autoencoders, as explored by Vincent, 2011. They show how these approaches can be connected through score matching, which involves estimating the gradient of the logarithmic density ratio between two probability distributions. This research highlights the potential of DiffWave in audio synthesis and its ability to bridge the gap between different generative modeling approaches. The appendix section of the research paper is divided into 5 parts, each focusing on distinct aspects of piecewise deterministic Markov processes, PDMPs, and their time reversals. Appendix 8.1 provides a detailed construction of a non-homogeneous PDMP with multiple jump types, characterized by the triple phi, lambda, q. This involves defining the differential flow phi, proposals for next event time, selecting the next jump time, and process definition on the interval tn+1. Appendix 8.2 discusses the extended generator of a PDMP, as given by Davis, 1993, Theorem 26.14. The generator is defined as LTF, Z, equals nabla Z, plus lambda, T, Z, integral, F, Y, F, Z, Q, T, Z, die, for all functions f in the domain of LT. The Carré-Duchamp gamma T, F, G, is also introduced, representing the difference between the generator applied to the product of two functions and the sum of each function individually applied to the generator. Specifically, in the context of a PDMP with generator, 11, gamma T, F, G, Z, equals lambda, T, Z, integral, F, y, f, z, g, y, g, z, q, t, z, die. The remaining appendices cover various details and proofs related to the framework of density ratio matching, splitting schemes for simulating backward PDMPs, the proof for Theorem 1, and additional numerical simulations and results. The authors provide a proof of proposition 1 by applying Conforti and Leonard's theorem 5.7. This requires verifying certain assumptions, including the technical condition H4, which states that the closure of the convex hull of the range of the drift term is contained in the domain of the infinitesimal generator lieutenant for any time t. The authors verify the general hypotheses of Conforti and Leonard, which are satisfied since the vector field phi is locally bounded, the switching rate lambda is continuous, and the jump kernel Q is a probability distribution. The integral of the switching rate lambda with respect to the jump kernel Q is finite, as stated in equation 12. The authors also introduce the class of functions C2C, ROAD, and define a set F of functions that satisfy conditions 13 and 14 involving the infinitesimal generator LT and the Carré-Duchamp operator gamma t. They prove that F is equivalent to C2C, E, by showing that conditions 13 and 14 hold for any F in C2C, E. This involves bounding the integral of the infinitesimal generator lieutenant with respect to the measure micro 0 pt using the fact that F is compactly supported and the switching rate lambda is finite. The authors then turn to the proof of proposition 2, which involves rewriting the flux equation for a piecewise deterministic Markov process, PDMP, with position velocity decomposition in homogeneous jump kernel. They show that the flux equation can be simplified to an equation involving the conditional probability measure micro 0 pt, dw, y, and the switching rate lambda. The conditional law of the velocity vector, given the position vector at time t, is a fundamental concept in the study of piecewise deterministic Markov processes, PDMPs. This page delves into the intricacies of this concept, particularly focusing on two distinct cases for the flux equation. In the first case, the flux equation is defined as q, y, w, dx, dv, equals delta y, dx, delta ryw, dv. Here, delta y, dx, denotes the Dirac measure at y, and delta ryw, dv, represents the Dirac measure at ryw. This specific form of the flux equation highlights the importance of the measure micro vref and its relationship to the probability densities pt, w, y, and pt, ryw, y. The balance condition, which ensures that the probability measure is preserved over time, is also discussed in this context. The second case introduces a different structure for the flux equation. Q, y, w, dx, dv, equals delta y, dx, nu, dv, y. In this scenario, nu, dv, y, is a probability measure on the velocity space, conditioned on the position y. This variation of the flux equation also emphasizes the role of micro vref and its connection to the probability densities pt, w, y, and pt, ryw, y, albeit with a different mathematical framework. Beyond these two cases, the page extends proposition 2 to encompass multiple jump types. This extension is crucial for understanding PDMPs that exhibit more than one type of jump. The backward jump rate and kernel are redefined to accommodate this complexity, ensuring that the balance condition remains valid for each jump type. This generalized approach provides a comprehensive understanding of the conditional law of the velocity vector in PDMPs, shedding light on the intricate interplay between position, velocity, and time. Deriving rigorous statements regarding time reversals of zigzag process, ZZP, Bouncy Particle Sampler, BPS, and Randomised Hamiltonian Monte Carlo, RHMC, is the focus of this section. The authors rely on proposition 2 and verify its assumptions to achieve this. Specifically, for ZZP and RHMC, they assume the technical condition H4, which can be proved using techniques from Durmus et al., 2021. The time reversal of ZZP is presented in proposition 4, where the vector field is given by left-pointing arrow minus phi z, x, v, equals, minus v, 0, t. The jump rates and kernels are derived for all y, w, element of R2D such that PTF minus T, w, y, greater than 0. The proof involves verifying the conditions of proposition 2, relying on the locally bounded vector field phi, x, v, equals v, 0, t, and the non-explosive nature of the ZZP. The authors also establish an upper bound for E, partial differential I psi, xt, using the mean value theorem and the assumption of continuous differentiability of psi. Proposition 5 deals with the time reversal of BPS, where the vector field is given by left-pointing arrow minus phi b, x, v, equals minus v, 0, t. The jump rates and kernels are derived, and a density pt, w, y, is defined. The authors assume E micro, nabla psi, x, less than infinity and show that the time reversal of the BPS satisfies the required conditions. In both propositions, the authors provide a detailed derivation of the time reversal of the respective samplers, highlighting the vector fields, jump rates, and kernels. They also rely on technical assumptions and existing results from the literature to establish the desired properties. The assumption of nu as the uniform distribution on the sphere is crucial for understanding the backward refreshment rate. This assumption leads to the proof of proposition 2, which verifies general conditions and analyzes deterministic jumps and refreshments. The time reversal of RHMC is also discussed, including the vector field and jump rates. Furthermore, the Bregman divergence approach for density ratio matching is emphasized, highlighting the minimization problem and its connection to Hyverinen's loss. The minimization of a loss function, comprising KL divergence and square loss, is crucial in machine learning. This loss function is intricately linked to the independence of the true density ratio. Hyverinen's ratio matching provides a vital connection between the loss and Bregman divergences, a fundamental concept in information geometry. In proposition 3, we establish the equivalence of the loss function to a specific Bregman divergence. This is demonstrated through a rigorous proof, which involves mathematical derivations and connections to existing frameworks. The equivalence is rooted in the fact that the Bregman divergence can be expressed as a convex function of the density ratio. The loss function's minimization is thereby transformed into an optimization problem, where the goal is to find the density ratio that minimizes the Bregman divergence. This formulation enables the application of various optimization techniques, such as gradient descent, to solve the problem. By leveraging Hyverinen's ratio matching and Bregman divergences, our approach provides a novel perspective on the minimization of the loss function. This perspective facilitates a deeper understanding of the underlying mechanisms and opens up new avenues for research in machine learning and information geometry. Algorithm 1 outlines the DJD splitting scheme for the time-reversed reversible Hamiltonian Monte Carlo, RHMC, a key component in the discretization of backward PDMPs. It begins by initializing either from a joint distribution pi, dx, p theta asterisk operator, dv, x, tf, or a product of target and velocity distributions pi, dx, nu, dv. The algorithm iterates through n steps, where each step involves applying a half-step of the Hamiltonian flow phi h, followed by an estimation of the ratio s between the target and proposal densities. A proposal tau n plus 1 is drawn from an exponential distribution with rate s lambda r, and if this proposal is accepted, a new velocity ev is sampled from the conditional proposal distribution p theta asterisk operator, x, et. The algorithm concludes with a half-step of the Hamiltonian flow to obtain the updated state, xtn plus 1, vtn plus 1. Algorithm 2 details the DJD splitting scheme for the time-reversed zigzag process, ZZP, another type of PDMP. This algorithm starts with initialization from the joint distribution pi, dx, nu, dv, and iterates over n steps. Each step involves calculating an intermediate position x and velocity ev, estimating the density ratio s theta asterisk operator, x, ev, et, and applying multiple velocity flips with probabilities based on the estimated ratio. The algorithm updates the state, xtn plus 1, vtn plus 1, using the intermediate position and velocity. In the case of the time-reversed Bouncy Particle Sampler, BPS, two possible splitting schemes can be used. RDBDR, as recommended by Bertazzi et al. 2023, or DJD, which involves simulating reflections and refreshments in the J part of the splitting. The RDBDR scheme is presented in algorithm 3, which includes refreshments, deterministic motion, and bounces. This scheme reduces the number of model evaluations compared to DJD. These algorithms are essential for the discretization of backward PDMPs, allowing researchers to simulate these processes efficiently and accurately. They provide a foundation for further analysis and applications in various fields of machine learning and statistics. The splitting scheme RDBDR for the time-reversed BPS algorithm is a pivotal component of the proposed methodology in this paper. It initializes either from a joint distribution pi circled times nu or pi, dx, p theta asterisk operator, x, tf, and iterates through a series of steps involving velocity updates, density ratio estimation, and position updates. The algorithm's purpose is to approximate the target distribution pi, dx, p theta asterisk operator, x, tf, using a sequence of proposals generated by the BPS algorithm. The discussion then shifts to the proof of Theorem 1, which provides a bound on the total variation distance between the target distribution and the distribution of the BPS algorithm's output. This bound is crucial for establishing the efficacy of the proposed splitting scheme. The proof begins by noting that the total variation distance can be written as the difference between two time-reversed PDMPs, one with characteristics phi, lambda, q, and another with characteristics minus phi, lambda, q. An intermediate PDMP is introduced, sharing the same characteristics as the original but with a different initial condition. The triangle inequality for the TV distance is applied to split the bound into two parts. One involving the difference between the target and intermediate PDMPs, and another involving the difference between the intermediate and original PDMPs. The authors employ the data processing inequality to bound the second term in equation 18, yielding a bound for the total variation, TV, distance between the target distribution micro and the distribution L, xtf, of the position at time tf. This bound comprises two terms, where the second term is bounded using assumption H2. The primary focus lies in bounding the first term, which involves Markov semigroups PT, left-pointing arrow minus PT, and EPT, as well as the probability distribution QTF. Utilizing the coupling inequality from Durmus et al. 2021, Theorem 11. The authors bound the TV distance between the distributions of two piecewise deterministic Markov processes, PDMPs, with identical initial conditions and deterministic motion, but differing jump rates and kernels. This bound is expressed in terms of the probability of the two PDMPs not being identical at time tf. The authors then rewrite the bound in terms of the function gt, which depends on the jump rates and kernels of the two PDMPs. By employing the synchronous coupling of the two PDMPs, the function gt is bounded, and the resulting bound is expressed in terms of the expectation of an exponential function of the integral of gt over time. In the context of the Zig-Zag process, ZZP, the authors upper bound the function gt, focusing on the first term, which involves the difference between the jump rates and kernels of the two PDMPs. This bound is expressed in terms of the supremum over a set A of the difference between the jump rates and kernels, normalized by the sum of the jump rates. The analysis of the proposed algorithm relies on deriving an upper bound for the function g1, which is achieved by applying the triangle inequality and leveraging the non-negativity of lambda z. This bound is given by a constant multiple of the sum of absolute differences between the terms left-pointing arrow minus lambda zi and lambda zi, where lambda zi is a function of x, v, and t. Furthermore, it is demonstrated that the function gt is also bounded above by a constant multiple of the same sum of absolute differences. This result is obtained by expressing the absolute difference between left-pointing arrow minus lambda zi and lambda zi as the product of rzi s theta I and lambda zi, where rzi and s theta I are functions of x, v, and t. The paper then utilizes the inequality 1 e caret z is less than or equal to z, which holds for z is greater than or equal to 0, to derive an upper bound for the expectation of a certain exponential function involving gt. This bound is crucial in the analysis of the proposed algorithm. The experimental setup consists of 50 Cascade Lake Intel Xeon 5218-16 cores, 2.4 GHz, with each experiment taking between 1 and 5 hours to complete. The datasets used include the Gaussian grid dataset, and the model architectures employed are ZZP and IDDPM, which utilize neural networks with skip connections, and RHMC and BPS, which leverage neural spline flows. The implementation details of the neural networks include the use of batch normalization, the number of training and testing samples, and the model sizes. Additionally, the activation functions, layer sizes, and conditioning mechanisms are specified. Researchers have implemented various processes for generating data, focusing on the use of backward PDMPs with splitting schemes and IDDPM. To evaluate these methods, experiments were conducted using PyTorch, with the Atom Optimizer and a learning rate of 5e4 for all neural networks. The impact of refreshment rate, time horizon, and design choices on data generation accuracy was assessed. Results show that higher refreshment rates generally lead to better data quality, as measured by the 2 Wasserstein metric, with accuracy presented in Table 3. Similarly, longer time horizons tend to produce more accurate results, as demonstrated in Table 4. Figure 3 illustrates the generated data from the best model for each process, showcasing the effectiveness of the proposed methods. The paper also explores the task of generating handwritten digits using the ZZP process on the MNIST dataset. Figure 4 displays promising results obtained with a U-Net architecture, featuring hidden layers of 128,256,256,256, 2 residual blocks at each level, and a self-attention block at a resolution of 16 × 16 with 4 heads. The network parameters include an exponential moving average with a rate of 0.99, the CLU activation function, and soft plus output activation with beta equals 0.2. The model was trained for 40,000 steps with a batch size of 128. These results demonstrate the potential of the proposed methods for generating high-quality data. The generation process for various datasets, including checkerboard, ZZP, RHMC, BPS, IDDPM, fractal tree, Olympic rings, rows, and Gaussian mixture, is a crucial component in the research. Each dataset serves as a testbed for evaluating the performance of the proposed methods. The figure illustrates the diversity of these datasets, showcasing the complexity and richness of the data used for experimentation. This variety is essential for a comprehensive evaluation of the research's objectives. The 00-point ZZP model, when trained on the MNIST dataset, demonstrates exceptional generation capabilities as depicted in Figure 4. This figure showcases the model's ability to generate high-quality images that closely resemble the training data. The ZZP model, a novel approach to deep learning, eliminates the need for traditional backpropagation and gradient descent algorithms, instead utilizing a self-supervised learning mechanism based on energy minimization principles. The generated images are arranged in a grid format, highlighting the model's capacity to produce diverse and realistic digits. Each image represents a different digit from 0 to 9, demonstrating the model's understanding of the dataset's structure and variability. The quality of the generated images can be assessed by their clarity, coherence, and similarity to the actual MNIST images, which appear sharp and well-defined, indicating successful learning of the underlying patterns and features of the dataset. The diversity among the generated images suggests the model's capability to capture the range of variations present in the training data. This achievement challenges the conventional wisdom that backpropagation and gradient descent are essential components of deep neural networks, opening up new avenues for exploration and development in the field of machine learning.